Salutations, dear viewer. Good time zone. Welcome back. I want to start out by clearing up something that I had said from the previous episode, in that I believe I called it a two-parter that we were going to be starting on. Allow me to elaborate on that. When I said that, I figured, oh, I just have one idea left to derive and communicate to you, and then we can do an example. How long can that possibly be? Well, it turns out almost 40 minutes. When I hit the stop recording button, it said 39 minutes and change, and that presented me with two options. Option A, I could try to slog through editing all of that in a few days' time, and then put up subtitles for it, and then at the end of the day still present to you a video that is perhaps a little bit too long to comfortably sit down and watch. Or option B, I could do a three-part thing instead, where I break it up into a perhaps slightly too short video detailing the last topic, and then a whole video dedicated to the example that will cover the three ideas that we just covered. And I liked that a lot better. So that is where we are now. Transitioning away from that, I have recorded, or I've written down, the angular momentum equation that we derived, as well as the outbound angle and turning angle equations that we derived from our last episode. These will be useful in what is now the next episode, but let's focus on one last topic, that being hyperbolic excess speed, which I will denote as V infinity. And as I see it, let me consciously make that look more like a V as opposed to a gamma. You're welcome. So V infinity, hyperbolic excess speed. What is it? In theory, this is the amount of speed that you will have when you reach an infinite distance on your hyperbola. So you are on a trajectory to leave the system. When you reach an infinite distance, this is the speed that you will have. In practice, this is effectively the speed that you will have when you reach the edge of the host body's sphere of influence. I say effectively. When you reach the sphere of influence, you will be at a finite distance. Your speed will be a little bit higher. It is not going to be a perfect representation, but for a back-of-the-envelope calculation, it's good enough. So this actually reminds me of one thing that I would like to share with you. When it comes to hyperbolas, hyperboloses is most definitely wrong, and we are going to move very far away from that. When you are dealing with hyperbola, this excess speed that you will find here is actually also the excess speed that you will have, or well, I say the excess speed. It is your starting speed and your ending speed. This is because, once again, gravity is a conservative force, and this is a conservative system. So the only thing that changes throughout all of this is just the direction of your velocity, not your magnitude. Now that I have done that, This is probably something that you would be able to pick up on your own. However, I'd feel better having it explicitly said it. Oh, one last thing. There we go. All right, bring that back down to 4. Off eraser. Awesome. So, if you want to look at hyperbolic excess speeds, the best place to do that is going to be specific energy. I'm actually going to write it over here. Equals v squared over 2 minus mu over r. And what happens when you take the limit of this system, of this equation, when your radius gets to an infinite distance? Well, let's take a look. We have our energy is equal to v squared by 2. Any number, regardless of how big it is, divided by infinity becomes 0, which leaves us with only this section of our equation. Since this is at an infinite distance, I will denote it as v infinity. Oh, look at that, hyperbolic excess speed. And I probably don't have to do this, but I'm going to denote our energy as the energy that we have at infinity as well, our hyperbolic excess energy. And off the top of my head, I don't know if hyperbolic excess energy really comes up in anything explicitly, but it is useful for the next set of equations that we're going to be using. However, really quick, speaking of explicitly stating something, I feel better having written that down, and that is the story of our hyperbolic excess speed. Now I'm going to scroll down a little bit. I'm going to leave that boxed equation up, and I would like to explore something else. So we did bring up that I did mention earlier that energy is conserved. Gravity is a conservative force. This is a conservative system. Energy is not going to be randomly introduced or taken away. So with that in mind, the energy that we have at an infinite distance is the same energy that we have at the finite within sphere of influence distance. So when you expand that, so we know what this is, we just found it. V infinity squared by 2. And then we know what that equation is. That is v squared by 2 minus mu over r. And I'm starting to see something come together from this. Let's get one step closer to solving for v infinity. So if we multiply both sides by 2 mu over r. And yes, this is looking good. I see our hyperbolic excess speed. I see a total velocity, and that's ringing some bells for me. If I go over to here, where is it? Here we go. Aha, our escape velocity. The square root of 2 mu over r. 2 mu over r. That, if you will allow me to write this down here again, is our v escape squared. Writing this up another way, our total velocity is equal to our escape, well, our total velocity squared is equal to our escape velocity squared. That's only, yes, there are 2 e's in escape, but it doesn't go there, plus our excess hyperbolic speed squared. And that's pretty straightforward. That's not too bad. I'll go ahead and I will box both of these, even though I'm really probably only going to use that one in the future, just because I like how general it is. It's very Pythagorean, and I like that about that equation. All right. We have one last thing. Oh, really two last things I want to cover. So the first, if I were to redraw, make sure that I have the right color up. If I were to redraw my hyperbola, and I'll do zoop, zoop, there we go. And I have my filled focus and my empty focus. Whereas in an elliptical system, if I were to have filled and empty focus, the boundaries here, this is 2 times the semi-major axis. In hyperbola land, oh, how do I want to describe this? The rightmost point, basically, the innermost points of both hyperbola, if you take the distance between them, funnily enough, you will have 2 times the semi-major axis. Now, since we've been operating under the assumption of this is our datum and everything to the left is positive, this is a positive semi-major axis. This here is our datum because it is the closest point to our host body. But our semi-major axis is pointing to the right instead of to the left. As such, our semi-major axis is negative. So A is less than 0 here, which means that if we were to take the second specific energy equation, minus mu over 2A, well, if A is negative, then our energy is positive. Okay, that still checks out. That still works. Make sure that I include that this is indeed greater than 0. And, well, like I had said at the beginning of the video, this is going to be a shorter video, and the example will be, I think it's going to be an entirely dedicated video to that example. This mythic example that I keep alluding to. So I am going to go and get started on preparing that. But until then, I'd like to thank all of you for stopping by.